Hey everyone, welcome back to another video here on Try Hack Me. I'm John, and today we're going to be taking a look at the room Intro to LAN. Learn about some of the technologies and designs that power private networks. That being said, let's go ahead and dive right into task 1, introducing LAN topologies. Local area network, LAN topologies. We'll go ahead and click the view site. I think it's already loaded, but we'll just make sure. Over the years, there have been experimentation and implementation of various network designs. In reference to networking, when we refer to the term topology, we're actually referring to the design or look of the network at hand, so how everything's actually connected. Let's discuss the advantages and disadvantages of these topologies below. First, let's talk about the star topology. The main premise of a star topology is that devices are individually connected via a central networking device, such as a switch or a hub. This topology is the most common found today because of its reliability and scalability, despite the cost. Any information sent to the device in this topology is sent via the central device, which connects everything. Let's explore some of these advantages and disadvantages of the topology below. Because more cabling and the purchase of a dedicated networking equipment is required for this topology, it is more expensive than any of the other topologies, and we'll discuss a few more below. However, despite the added cost, this does provide some significant advantages. For example, this topology is much more scalable in nature, which means that it is very easy to add more devices as the demand for the network increases. Unfortunately, the more the network scales, the more maintenance is required to keep the network functional. This increased dependence on maintenance can also make troubleshooting faults much harder. As there's more places, there's more cables, there's more things to go wrong in general. Furthermore, the star topology is still prone to failure, albeit reduced. For example, if the centralized hardware that connects devices fails, these devices will no longer be able to send or receive data. Thankfully, these centralized hardware devices are often very robust. Switches, they don't die very often, and when they do, it's very obvious that they're dead, and it's pretty easy to replace them. They're usually not terribly expensive as well, as far as networking hardware goes. As you get ones with nicer features, they definitely go up in price, but for just a basic one for home use, they're like $25 or something like that, which on the scale of networking things, that's not too bad. But you can see in this how everything's connected via a central hub. Bus topology. This type of connection relies on a single connection, which is known as the backbone cable. This type of topology is similar to the leaf off a tree in the sense that the devices, or leaves, stem from where the branches are on the cable. Because all data destined for each device travels along the same cable, it is very quickly prone to becoming slow and bottlenecked if devices within the topology are simultaneously requesting data. This bottleneck also results in very difficult troubleshooting because it quickly becomes difficult to identify which device is experiencing issues with data all traveling along the same route. However, with this said, bus topologies are often one of the easier and more efficient topologies to set up because of their expense. And you can see that there's this big connecting thing that there's not a lot of cabling involved there because you just have one dedicated mega cable. Because of their expenses such as cabling or dedicated network equipment used to connect these services. So lastly, another disadvantage of the bus topology is that there is a little redundancy in place in case of failures. This disadvantage is because there is a single point of failure along the backbone cable. If this cable were to break, devices can no longer receive or transmit data along the bus. Let's talk about ring topology. The ring topology, also known as token topology, boasts some similarities. Devices such as computers are connected directly to each other to form a loop, meaning that there is little cabling required and less dependence on dedicated hardware such as networks or switches or things like that within the star topology. A ring topology works by sending data across the loop until it reaches the destined device. Using other devices along the loop will they'll forward the data, so essentially it just gets passed along these points. Interestingly, a device will only receive data from another device in this topology if it does not have any to send itself. If the device happens to have data to send, it will send its own data first before sending data from another device. Because there is only one direction for data to travel across this topology, often counterclockwise or clockwise, just one of the two, it is fairly easy to troubleshoot any faults that arise. So for example, if you had a break right here, and suddenly this device can't receive data from this device, well, fairly obvious that the cable's probably bad there. However, this is a double-edged sword because it isn't an efficient way of data traveling across a network, and it may have to visit multiple devices first before reaching the intended device. Lastly, ring topologies are less prone to bottlenecks, such as within a bus topology, as large amounts of traffic are not traveling across the network at any time. The design of this topology does, however, mean that a fault such as a cable cut or a broken device will result in the entire networking breaking or just failing altogether. One thing to note here, this is less common to see. This is something that you would probably see if you have a mesh network, that it might leverage a ring topology to pass things between those different nodes in the network. However, that's not exactly all that common. The one that you're likely to see in most cases is probably this star, just because it's very common, it's very easy, and often enough in your home network, this is probably what you're using anyways, where you have one router that has a Wi-Fi access point on it and everything connects to the same access point. So just be aware that this is probably the most important one, but you do need to know about these other topology types. Let's talk about what is a router. It's a router's job to connect networks and pass data between them. It does this by using routing, hence the name router. Routing is the label given to the process of data traveling across networks. So what do we mean when we say across networks? This means networks with different addressing schemes. So maybe I have a home network and you have a home network. But if I want to send something to you, maybe an email, that has to cross the public internet too. So we have our routers that sit on the edges of those networks. So where the internet comes into my house at what's called the demarc point, and then where it comes into your house at the demarc point there. And that does the translating. It handles how routes are created. And when I say routes, I mean general rules of how you can talk to devices across those networks. So it uses the destination as a means to break down where it needs to send things. Think of the old like turnstile where you'd see marbles going in and they would go out one specific end of maybe a marble contraption. It just routes things. And in this case, it'd be, instead of marbles, it would be packets. So uses routing rules to just control where it needs to send things. Routing is useful when devices are connected by many paths, such as in the example diagram below. So you can see that maybe this is the internet here in the middle, where we have my house and then your house here, and I'm going to send you an email, but it needs to go between those other networks, or maybe just different parts of a building. But you can see that these handle the translation so that this network can be its own thing, and this network can be its own thing as well. Let's talk about switches. Switches are dedicated devices within a network that are designed to aggregate multiple other devices such as computers, printers, and or other networking capable devices using internet, or Ethernet rather, so the actual cable. These various devices plug into a switch's port. Switches are usually found in larger networks such as businesses, schools, or other similar sized networks, where there are many devices to connect to the network. Switches can connect a large number of devices by having ports, groups of ports, 4, 8, 16, 24, 32, and 64 devices to actually plug into, and they can get even bigger than that. So generally speaking, they're going to come in this multiple of 4. Here, it's just because it's easier to make them and it's easier to address devices in that way. So these will not necessarily have routes such as routers do, but they have a way of actually identifying which device is plugged into that cable. And from there, it can kind of form a routing table internally where it knows how to send these packets along. So unlike routers, these devices do not perform routing, as I just mentioned, in the sense of directing paths along a certain route using IP protocol. Instead, switches use a technology called packet switching to break down pieces of data into smaller, more manageable chunks of data called packets. This technology allows for the efficiency of a network, or because large pieces of data take up more resources. If you want to send a large chunk, like maybe a large part of a game download at once, that's not very efficient. That's a lot of data traveling, and if you have to keep it all connected, that is potentially just going to take up the entire network, its processing. However, it's much easier to transmit that in small little bite-sized pieces. It's sort of the same concept as carrying up furniture, or if you need to, it's easier to break it down and carry light boxes rather than one really big item, as it takes everything or all of your resources at that point. And you can see again how it mentions the efficiency there. So both switches and routers can be connected together. The ability to do this increases the redundancy or the reliability of a network by adding multiple paths for the data to take. If one path goes down, another can be used. Whilst this may reduce the overall performance of a network because packets have to take longer to travel, there is no downtime. A small price to pay considering the alternative. So quick practical. Attached to this task is an interactive practical featuring the discussed LAN topologies, learning about the various ways in which they are vulnerable to breaking. Break the LAN topologies to retrieve the flag. So the first question here that we have is, what does LAN stand for? That is going to be local area network. What is the verb given to the job that routers perform? That should be routing. There we go. What technology do switches use to break down large pieces of data into smaller, more manageable packets? That is going to be packet switching. What topology is cost efficient to set up? Let's see. I'm guessing this is the bus topology. And there we go. What topology is expensive to set up and maintain? So that is going to be the star because you have more networking cables and things like that. And then let's go ahead and complete the interactive lab. Topology flaws. This lab will take you through the flaws in different network topologies. First, we have the ring topology. In ring topology, all devices are connected to two others to create a full circle. And then you can see packets of data travel from one device to the next until they have reached their destination. One of the major flaws with a ring topology is that if a device goes down or a cable is broken, then data will no longer be passed. If you hover over the middle of a network cable, you can cut it to see what happens to the actual packets. So here we have our scissors, and we cut it, and we can see that those are broken, and packets can no longer travel. The packets can no longer travel around the network, and no devices can talk to each other. Bus topology. With the bus topology, all devices are connected to a single cable, often called the backbone. Data is sent in both left and right directions down the backbone until the packet's destination is reached. A major flaw in bus topology is it cannot handle a large amount of data. On the next step, send as many packets as quickly as you can to try to take down the network. So we'll go ahead and just click this a lot, send a lot of traffic, and we'll see that very quickly this is going to start getting overwhelmed. And there we go. We can see it's now down because there's just too much stuff sitting on the network. And then we have this star topology. With the star topology, all devices are connected with their own cable to a central switch/hub. Every packet is sent through this switch, which means if the network goes down, if the switch goes down rather, the network will no longer work. See if you can somehow break the switch. And it looks like it's giving us a hammer. That's wonderful. And now we can see the network is down. And we've gone ahead and completed our practical. Let's go ahead and copy that over. Paste that flag, topology flaws, and there we go. Let's move into task 5, a primer on subnetting. As we've previously discussed throughout the module so far, networks can be found in all shapes and sizes, ranging from small to large. Subnetting is the term given to splitting up a network into smaller, miniature networks within itself. Think of it as slicing up a cake for your friends. There's only a certain amount of cake to go around, but everybody wants a piece. Subnetting is how you decide who gets what slice and reserving such a slice of this metaphorical cake. Take a business, for example. You will have different departments such as accounting, finance, and human resources. You need to somehow split up your network between these different departments, though. And here we can see we have a diagram demonstrating exactly that, where we have the internet with our router on the edge and then a switch connecting everything in a star topology. And then we can see this is further broken up where we have our individual sections, which is where subnetting comes in. Whilst you know where to send information in real life to connect or to the correct department, networks need to know this as well. Network administrators use subnetting to categorize and assign specific parts of a network to reflect this. Subnetting is achieved by splitting up the number of hosts that can fit within the network, represented by a number called a subnet mask. Let's refer back to our diagram on the first room in this module. And here we can see that we have our IPv4 address with the 0 to 255 octets. As we recall, an IP address is made up of 4 sections called octets. The same goes for a subnet mask, which is also represented by a number of 8 bytes, 32 bits, ranging from 0 to 255. Subnets use IP addresses in 3 different ways: to identify the network address, to identify the host address, and identify the default gateway. Let's talk about what these actually mean. Let's split these 3 up to understand their purposes in the table below. So first off, we have the network address. This is a bit of a confusing topic, but know that this is a very simple idea in concept. This address identifies the start of the actual network and used to identify a network's existence. So this is the network that sits at the start. You'll very rarely see this .0 address in use by a device because it belongs to the actual network. So for example, a device with the IP address of 192.168.1.100 will be on a network identified by 192.168.1.0 because that belongs to the network. This can be split up a little bit further, but just know that generally that 0 is going to be what identifies the network itself. Let's talk about the host address. An IP address here that is used to identify a device on a subnet. So this is just something that belongs to your device. So for example, a device will have the network address of 192.168.1.10. So this could be a device address with the network address still being this .0 up here. And you can see another example here where just that last octet is actually changing. Default gateway. The default gateway address is a special address assigned to a device that is capable of sending information to another network. So this is going to be a router. This is essentially how everything needs to go out. Think of if you are in a building that has one way out. That is your default gateway because that's how you need to exit the building or enter it. Any data that needs to go to a device on that isn't on the same network will have to go through this default gateway. These devices can use host addresses, but usually use either the first or last host address in a network. It's very common to see this be that .1. I believe I mentioned that either in the previous video or earlier in this room where this .1 is often enough going to be a router, or the .254 could be a router as well. Now, in small networks such as at home, you will be on one subnet as there is an unlikely chance that you need more than 254 devices connected at one time. However, places such as businesses and offices will have much more of these devices. So you have PCs, printers, cameras, sensors, and so on and so forth. And that's where you really need to have subnetting come into play. Subnetting provides a range of benefits, including efficiency, security, and full control of how the network is actually split up. We'll come on to explore exactly how subnetting provides these benefits at a later date. However, for now, all we need to understand is the security element to it because we're focused on becoming security professionals. Let's take the typical cafe on the street. This cafe will have 2 networks, one for employees, cash registers, and other devices for the facility. Hopefully this is on its own network because of PCI. I won't go too far into that. Generally speaking, your cash registers need to be on their own network. And then one for the general public. And hopefully there is no way that these can communicate because that's where you start having bad things. Subnetting allows you to separate these 2 use cases from each other, whilst having the benefits of a connection to a larger network such as the internet. So know that subnetting, generally speaking, is just how we can separate things off. That's really the big idea out of this section. What is the technical term for dividing up a network into smaller pieces? That is going to be subnetting. How many bits are there in the subnet mask? That should be 32. What is the range of a section octet of a subnet mask? That should be 0 to 255. What address is used to identify the start of a network? That would be the network address. What address is used to identify devices within a network? That'll be the host address. What is the name used to identify the device responsible for sending data to and from another network? That is going to be your gateway. That should be your default gateway here. And there we go. Let's move into task 3, the ARP Protocol. Recalling from our previous tasks that devices can have two identifiers, a MAC address and an IP address. The ARP Protocol, or Address Resolution Protocol for short, is the technology responsible for allowing devices to identify themselves on a network. Simply, the ARP Protocol allows a device to associate its MAC address with an IP address on the network. Each device on a network will keep a log of the MAC addresses associated with other devices. So think of it this way. Again, your IP address, that can change. You can swap houses with your neighbor. You can do whatever you want with that. But your MAC address is, in theory, globally unique. So you probably won't have the same MAC address as your neighbor. And that's something that can be used to identify you uniquely. So even if you move, you still have that MAC address. When devices wish to communicate with another, they will send a broadcast to the entire network searching for the specific device. Devices can use their ARP protocol to find the MAC address and therefore the physical identifier of a device for communication. Think of it this way. Yell out into a crowd and you say, I need the person with this specific MAC address. That person responds, hopefully, if they're not spoofing their MAC address. That's what ARP is doing. It's very simple, and it's just a way of trying to find that unique identifier. How does ARP work? Each device within a network has a ledger to store information on, which is called a cache. That is specifically the ARP cache. In the context of the ARP protocol, this cache stores the identifiers of other devices on the network. So once you've done that yelling out in the crowd to figure out who has what MAC address, you can check your cache because you've already done it before. Why do it multiple times when you know you're going to be sending a lot of data to and from that device? And that saves on network traffic because, again, remember, we only have so much data that we can send at once. We want to keep that as limited as we can just because we want to have bandwidth for other things. In order to map these two identifiers together, the IP address and the MAC address, the ARP protocol sends two types of messages. We have an ARP request, which is that yelling out into the crowd, and then the ARP reply, which is the person in the crowd yelling back that, hey, I have that. When an ARP request is sent, a message is broadcasted to every other device found on a network by the device that has it in theory, asking whether or not the device's MAC address matches the requested IP address. If the device does not have the requested IP address, an ARP reply is returned to the initial device to acknowledge this. The initial device will now remember this and store it within its cache. So again, we yell out and we say, hey, do you have this MAC address? Or hi, MAC address, do you have this IP address? And it'll reply back and confirm it. And then we have that cached. What does ARP stand for? That is going to be just up here at the top, and that is going to be Address Resolution Protocol. And again, that's just so that we can match IP addresses or MAC addresses up with IP addresses, and then there's reverse ARP, which does the opposite, where we can match an IP address with a MAC address. There we go. What category of ARP packet asks a device whether or not it has a specific IP address? That should be a request, as we're asking it. What address is used as a physical identifier for a device on a network? That is going to be a MAC address. And then what address is used as a logical identifier for a device on a network? That is going to be the IP address, because this is just the logical one. This can change. Let's move into task 4, the DHCP protocol. IP addresses can be assigned either manually by entering them physically into a device, or automatically and most commonly by using the DHCP Dynamic Host Configuration Protocol server. You do not need to know what this shortens to. That's just a fun little tidbit. You'll call this DHCP every single time. When a device connects to a network, if it has not already been manually assigned to an IP address, it sends out a request, a DHCP discover, to see if there are any DHCP servers on the network. So it says, hey, I don't have an address. Is there a server out there that can give me one? And you can see the problem with having multiple DHCP servers, because they might both reply, and it might have two IP addresses that are incorrect. The DHCP server replies back with an IP address the device could use, so a DHCP offer. The device then sends a reply confirming it wants the offered IP address, the DHCP request. So it says, hey, I like what you offered. I want to actually formally request that one. And then Lastly, the DHCP server sends a reply acknowledging that this has been completed and the device can start using the IP address. So it'll send back an acknowledgement, and we can see that broken down here, where we have, hey, I just joined this network, who can give me an IP address? The server itself is going to say, sure, let me go ahead and give you this one. Does that work for you? Yes, that works. I would like to formally request that one. And then it acknowledges it. And usually you have a default time span of 24 hours for that. Let's move into the actual questions here. What type of DHCP packet is used by a device to retrieve an IP address? That is going to be a DHCP discover. What type of DHCP packet does a device send once it has been offered an IP address by the DHCP server? That is going to be DHCP request, because we've already been offered it. We want to say, hey, this is my formal acceptance of it. I do want this address that you've given me. Finally, what is the last DHCP packet that is sent from a device, to a device rather, from the DHCP server? That is going to be our acknowledgement that says, the server says, hey, I see that you're requesting this. I'm acknowledging that request, and I'm going to formally accept it. And that will be the DHCP acknowledgement. Let's move into task 5, continue your learning with the OSI model. Continue your learning by joining the OSI model room. Highly recommend doing that right after this. If you have any questions, we'll go ahead and mark this as complete. If you have any questions, as always, I will have the Try Hack Me Discord and subreddit linked in the video description below. But otherwise, until next time, happy hacking.